So the formal definition for a type 1 error is when we reject the null hypothesis, but the null hypothesis is true. For me, that's kind of hard to think of. So that's why I think of it in terms of we see a statistically significant effect, but there actually isn't one there. The illusion error. That's how I like to think of type 1 error. Contrast this with a type 2 error, the invisibility error. This is when there is an actual effect there, but we don't see it. We rule that there is no significant effect. The actual effect is invisible to us, and we make a type 2 error. The formal way to say this is a type 2 error is when you fail to reject a null hypothesis when it is false. Again, that doesn't mean, it's hard to remember in my brain. So I just say type 2 error, we did not see anything significant, but there actually is significance out in the population. It's just invisible to us in our study. So these are the two errors. We're going to focus on the type 1 error for a second. So you might be asking yourself, well, we're talking about p-value adjustment. So why are we talking about this error, the different errors we can make with our hypotheses? Well, in summary, the reason is think about what the p-value is. It's the probability that we obtained the observed result, or something more extreme, assuming the null hypothesis is true. We accept a certain probability as being significant. We say 5% or lower. But what that means is we accept that if the probability is 5%, 4%, 3%, 2%, we accept that we might be wrong. We just know that when the p-value is small enough, it's unlikely that what we got is true under the null model. But remember, the p-value is still just a probability that we observed what we got under a null hypothesis. But it's still a probability that, yeah, if the null hypothesis is true, then some p-value percent of the time, we're going to see the observed results that we got. This connects to our alpha level. Our significance level is the percentage of the time we are okay saying we might be wrong in rejecting the null hypothesis. Because we're saying we're okay if there's a 5% probability or a 4% probability or 3 or smaller. We're okay saying reject the null model. But what if we ran a study and we got a significant result, say p equal to 0.01, but what if that was truly due to random chance and the null hypothesis is true? That's a type 1 error. So our errors connect to our p-values because our significance level, our alpha level, is called the type 1 error rate. It is the percentage of our results that we say are significant that probably are not statistically significant. We accept that 5% of the time, our significant determination is going to be wrong. That is a type 1 error, and alpha determines how often we make it. So if we do not want to commit a type 1 error that often, if we want to be more conservative, we could set the alpha level to 0.01 and say, hey, I want high significance. I want 1% on my p-value or smaller. That way, I'm only committing a type 1 error 1% of the time. That way, I'm only seeing an illusion and saying it's significant 1% of the time. And we can be a little more liberal. It's an alpha equal to 0.1 or 10%. And say, I'm okay making a type 1 error 10% of the time. I'm okay calling an illusion statistically significant 10% of the time. We'll get into it later in the course why it's 0.05. But 0.05 alpha, that is called our individual type 1 error rate. That's a big point. Read through this. Ask me questions. But that's where this connects. So why do we suddenly care about the fact that alpha is this, how often we make a type 1 error? Well, remember when we did regression, we really just looked at one model and one set of results and looked at, one F statistic. Here's the issue with ANOVA. When we start to do all possible pairwise comparisons between my study groups, we are, in a sense, carrying out multiple hypothesis tests in one situation. The alpha equal to 5% is the type 1 error rate in one comparison. Just one. That means I set alpha equal to 0.05. Going back to my heart rate example, remember I had the study groups of walking, running, and sitting. And I can find the mean difference in heart rate between those three groups in a set of pairwise comparisons. So if we look at each of those three pairwise comparisons, I get a p-value and a t-statistic for my walking minus running with an alpha level of 0.05. I can get a p-value and a t-statistic between walking and sitting at an alpha level of 0.05. And I can get a p-value and a t-statistic between sitting and running at an alpha level of 0.05. Well, wait a second. If it's 5% here, probability of committing a type 1 error, 5% here, and 5% there, well, eventually I'm going to get one wrong, right? If I did 100 comparisons, well, I know 5% of them, if I did 100 comparisons, if I had enough study groups to do 100 comparisons, and I ruled all 100 of them statistically significant at the 5% level, then that means 5% of those statistical significant claims should be wrong. And 5 out of my 100 statistically significant tests are actually insignificant, and I've committed a type 1 error. So the problem is, once we start to compare more than, two groups, once we start doing multiple comparisons, our probability of committing a type 1 error is no longer 5%. The probability compounds because it's 5% here, 5% here, and 5% here. 5% is just the individual rate. What about the probability of committing a type 1 error for all of these things? So that's a probability question, and I'm not going to have you do it or solve it or get into that. But what we know is that if it's 5% here, 5% here, and 5% here, it's not 5% across the combination of all of these things. The probability that I've made a type 1 error when I look at all my multiple comparisons is suddenly bigger than 5%, just because the probabilities compound. The probability or the chance that we make a type 1 error across all these comparisons is called the family-wise error rate. Remember, we're moving on from just an individual comparison to all possible group comparisons. And the more comparisons I make, the higher my chance of committing a type 1 error. The individual probability is 5%. The family or the group probability is larger than 5%, and it is some family error rate that is larger than 5%. So, wow, if we're doing a ton of multiple, group mean difference comparisons, and the probability that we make a mistake is increasing with the more comparisons we make, what do we do about that? We adjust the p-value. Dun, dun, dun. That's the big answer. Again, when we run multiple group comparisons, we need to account for the fact that the more comparisons we run, the greater our chance of making a type 1 error. So we engage in one of many procedures to adjust the p-value. And in short, just high-level summary answer, we do something to make the p-values bigger because we want to make it more difficult to reject the null hypothesis. Remember, a type 1 error is rejecting the null hypothesis when we should not. So in order to combat that error, we want to make it more difficult to reject the null hypothesis. As a result, we can tell R to carry out a procedure to inflate the p-values to reflect the probability of making a type 1 error across multiple comparisons. And that's really all it is. We tell R a specific thing, a specific kind of adjustment, and it makes the p-values on particular comparisons go up. That's all there is to it. So what is it exactly done to adjust the p-values? Well, I'll say this, and this is where I'll just kind of give you a short answer and encourage you to read more about it because it's a whole big separate topic that I just want you to know how to use it and in general what's going on, but you could read about all the different ways. There are so many different ways to adjust p-values, and I've listed many of them here. There's the Holm method for p-value adjustment, the Hochberg, the Hamel, the Bonferroni, a bunch of other ones. And I put a link here if you want to read about how mathematically the p-values are adjusted. You can absolutely go ahead and do that. I encourage you to do that. But in general, what it's doing is it's saying start at my regular alpha level of 0.05. Then based on the number of comparisons I'm doing, and based on the mathematics of whatever approach it is, change the alpha level to something smaller. We don't know what it is. It's dependent on what method we use. You can go through and calculate things. But basically, use some particular kind of adjustment, whatever one it is, to adjust the alpha level. Then increase the p-values such that we can still interpret them at the 0.05 level. So it's kind of weird, but p-value adjustments actually adjust the alpha level behind the scenes. But then to make it easy so that we can still interpret at our usual 0.05 level, it just does math to convert that into increasing the p-values. So lastly, the important part of this is that, so the method I use, Bonferroni, is the most conservative. It inflates p-values the most. And people often don't prefer that because they think it makes it too insignificant. But I like using the most conservative method. The other methods are less conservative. They don't inflate the p-values as much. And there's no best adjustment. You just got to go through and read and understand each of them to see which one works for you. But I don't care which one you use in this class. I use the Bonferroni. And that's what I like.